Okay, right. Let's see if we can do this. Right, can we see that clear enough? So if we just do this, then I can just share it with the others so it's easier for them to catch up. Okay, so our new equilibrium constant today is Kp, and this is then linked with the partial pressures that were referenced in those Le Chatelier questions. So essentially, this is just enabling us to work out what effectively is the concentration of a gas, when actually what we measure about gases is pressures rather than concentrations. All right, but to all intents and purposes, it's doing exactly the same thing here. Okay, so key bits we need to realise there. So pressure is proportional to the number of gas molecules in a container. So if the pressure is caused by particles bombarding the walls of the container, so if we increase the number of particles, we have a greater pressure. But we can also separate out the pressure that one particular gas would cause if it was the only thing and you took everything else away from a mixture. And that's what we call the partial pressure. So it's kind of the part of the total pressure that is caused by one individual gas. So we can do a little diagram. There's a kind of pretend bit here. So if we had 10 molecules all together, let's have 3 of them being coloured in ones. So can we draw your 3 coloured in particles? And then you can have 7 not coloured in ones. 1, 2, 3, 4, 5, 6, 7. And then we could think then about what the partial pressure is going to be. So out of our 10 molecules, how many of them were coloured in? 3. So that means 3 out of 10 of our particles were contributing to our total pressure. Okay, and that is then the partial pressure of that particular coloured in gas that we've got here. So 3 out of 10 times 2 is 6 over 10, which is going to be 0.6. So we could say that our partial pressure of our coloured in gas is 0.6 atmospheres. And then our partial pressure of our not coloured in gas is going to be the rest of it. So it's 7 out of 10 particles contributing to the overall pressure of 2 atmospheres. And that is then going to be 14 over 10, which is going to be 1.4 atmospheres there. Anything that we can spot about our 2 partial pressures? Absolutely, they add up to the total pressure. All right, so it's always worth using that as a quick check. So the sum of the partial pressures must add up to the overall pressure. So what we can say then in general terms is that partial pressure is equal to the number of moles of whichever gas you're interested in, divided by the total number of moles of that gas, times by the total pressure. And this part here, the number of moles of a particular gas divided by the total number of moles of gas, we can also call the mole fraction. Just sort of does what it says on the label kind of job, all right? The fraction of the total number of moles that are that particular gas. And then I put a note down there. So MB, the sum of the partial pressures is equal to the total pressure. So it could be that maybe you're given 2 out of 3 partial pressures and you just have to do a subtraction to work out the third one. Now look out for units and just make sure you take on board the units that are given to you in a question. So when we were looking at this one, our partial pressure here, our total pressure was given in atmospheres, so our partial pressure are in atmospheres. You could be given kilopascals, pascals, or atmospheres, and then they'll just be the same as you're working through them. So we've got our Haber process here. So just like we have with our KC calculations, you could be given moles at the start and 1 set of moles at equilibrium and then have to work out the rest of your moles at equilibrium. So we know how to do that now. This is just kind of working forward from there. So if we have a look at this here, can we then work out, please, the partial pressure of nitrogen, hydrogen and ammonia? And then we'll have a look at how we write out a Kp expression. Almost there with the numbers. Okay, so have we got our partial pressure of nitrogen as 0.4, I put 0.40 atmospheres. Yep. And our hydrogen 1.49. And ammonia 0.11. Okay, now when we are writing our KP expression, we use exactly the same idea as we did with KC, and that it's products over reactants raised to the power of their balancing in the equation. But this time we need to make sure we're writing down partial pressures instead of concentrations. So to do that, we put a P for the partial pressure. And so on the top, we're going to have the partial pressure of ammonia. So put P, and then in round brackets, sometimes you see no brackets at all, but most definitely not square brackets. We can put our ammonia and then put squared, because we've got the 2. And then in the bottom, same idea, but for the reactants. So we've got the partial pressure of hydrogen cubed and the partial pressure of nitrogen. Why can we not have square brackets? What do square brackets mean? Concentration. Okay, and this isn't concentration. All right. Then just like with KC, we can then put in our numbers here, but we also need to make sure we work out the units at the end as well. So we'll do that in a sec. So for this calculation, we're going to have 0.11 squared over points, I've just put them the opposite way around, but 0.4 for the nitrogen and 1.49 for the hydrogen cubed. And if you were to put that in your calculator, 9.1 times 10 to the minus 3. What's the units going to be for this one? Yeah, well done. So atmospheres to minus 2. So if we're working that out, we've got partial pressure squared. So you could put atmospheres times by atmospheres divided by atmospheres cubed. So write it down 3 times. Times by another partial pressure, atmospheres. So cancel, 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 cancel. So we've got 1 over atmospheres times atmospheres. So 1 over atmospheres squared is equal to atmospheres to minus 2, like that. Okay. Or if you don't need to go through the long-winded way, then you can just kind of cancel by just looking at that. And it doesn't really matter how you approach it as long as you get the right answer there. Okay, so note to the bottom here. So units for KP must be found for each reaction, exactly the same as KC. Only gases have partial pressures, so only gases feature in the expression for KP. So if you had a solid, it just wouldn't be there because there's no partial pressure. And so anything that is not a gas is just ignored then. Right, so let's have a look at the example on the other side. I've kept this one fairly straightforward in that we haven't gone through needing to work out what's present in the first place again. Okay, so if we are going through the whole question then, so it says a mixture of 0.165 moles of NO2 and 0.035 moles of N2O4 is at equilibrium at 350 Kelvin. Okay, so that is your equilibrium mixture. So we could even just go through and put that in straight away. So N2O4, we had 0.0335 and NO2, we had 0.165. Okay, so it's just worth putting moles at start if it's applicable. It's not here, just moles at equilibrium, and having that set out from the beginning. Okay, now because we're going to need to work out the mole fraction, what other number do we need here? Yeah, so we need the total number of moles. So probably if you get in the habit of putting that to the right hand side as well, then you've got that ready. So that's going to be 0.200 there. Okay, I'd always write equations to show what you're doing. So partial pressure is going to be equal to the moles of the gas you're interested in divided by the total moles of gas times by the overall pressure. And then we can go through and work that out for the two different gases we've got. So we've got partial pressure of NO2 and we've got the partial pressure of our N2O4. So can you work out your two different partial pressures, please? Okay, so we've got the numbers up on the board there. So NO2 0.825 atmospheres, N2O4 0.175 atmospheres, and just double check they add up to the total pressure of 1. And then work out your KP expression and then work out your final answer. So for our KP expression here, we've got the partial pressure of the NO2, and that's going to be squared because we've got a 2 in the balanced equation, divided by the partial pressure of the N2O4. We have our 0.825 squared over 0.175, and that gives us 3.889. And how many significant figures should we be quoting this to? So we've got 3 and 2. 2. Yeah, you could possibly also argue 1 because the total pressure was only given to 1 atmosphere. So the pressure is 1 atmosphere, so that's just 1 significant figure. The NO2 was 3 sig figs, the N2O4 was 2 sig figs. So strictly it should just be 1 here. So if we go 4, and then what are our units going to be? Yeah, it's just going to be atmospheres. So to 1 sig fig. You could put a note there. So as pressure is given to 1 sig fig. So if you're kind of looking back later and wondering why we rounded it to 1 sig fig. So remember, always look for the least accurate piece of information in your question. Okay, right. Next thing then is to practice this. And so we need the gaseous equilibrium questions.